All right, hey guys, we're going to talk about periodic families now. I was going to make 10 really short videos on each family, but I figured one long video would probably be better, so you're not like flipping through different things. Let's go ahead and get started. Oh, I need to share my screen. Okay. So we learned about groups and periods. Now we're going to start talking about families, which are actually, I like this periodic table because it's color coded. Unfortunately, your periodic table on your exam will not be color coded. So make sure that you have an idea of where these are. At the end of the day, you are responsible for knowing this, okay? And I'm not going to do anything to trick you. So just FYI. So the first group is group one. I'm sorry, I forgot to say that. We're going to start with group one, or the first group, which is the alkali metals. And they're from lithium all the way to francium in red. So they are really soft and shiny, and they have very, very high melting points, which probably means that they're in the solid phase most of the time, because when we melt something, we go from solid to liquid. And most of them are metallic in color. They are highly reactive at standard temperatures. I remembered one day my chemistry teacher in high school like put a piece of sodium in water and it like blew up and it broke the glass and there was like a little fire and he was like freaking out and we were like, okay. And then he like covered it in sand. It was really weird. They have a very extremely unstable atomic structure. And you should know why they have an extremely unstable atomic structure. And that is because in this in this group, they do not have an entirely filled s orbital. So those electrons that electron that's in the s orbital can move. Remember, we end with a whatever S1, which means that the s orbital is not filled. And that's why they're mostly found with a positive charge. If we remove an electron, then it has an entirely filled p orbital, and therefore it's a little less reactive. And again, these are from lithium all the way to francium on group one, periods 2 to 7, not 1 to 7. We'll fix that. Now we're going to talk about the alkaline earth metals, which are here in orange, from beryllium all the way to radium. Group 2, again, should be period 2 to 7, I apologize. They are shiny and silvery white in color. It's very hard to tell them apart from one another. And they are somewhat reactive at standard temperatures. They're fairly stable when it comes to atomic structure because they have an entirely filled s orbital. Most of them are found with a 2 positive charge. So like, magnesium 2+, radium 2+. If we remove 2 electrons, then our valence electrons become 8. And these are in group 2, again, from periods 2 all the way to 7. Now we're going to talk about transition metals, arguably the most fascinating and biggest family on the periodic table. They're in groups 3 to 12, periods 4 to 7. And their physical characteristics, they're variable. They can look like liquids, they can be gold, they can be silver, they can be dull, they can have a really high luster. But most of them are solid at room temperature, with the exception of mercury. Especially if you've ever seen a mercury thermometer, you know that that's liquid at room temperature. They have very, very, very high densities. Density is a great component of solid structures. Transition metals have very high densities, almost like over 100 grams per milliliter, which is a lot, compared to water, which is 1 gram per milliliter. These are metals, so they can form metallic bonds, which means they bond between metals and other metals. And of course, if we have more than one, we have a compound. Some are good conductors and some are bad conductors. Again, you should know this. We know conductors can donate electrons. And if these don't have an entirely filled p orbital, that means that some of the electrons can move and go to excited states or be donated. And that's really why chemistry becomes a really big part of electricity, knowing how these metals and transition metals form. And again, right in this area, groups 3 to 12, and then periods 4 all the way down to 7. Next, we're going to talk about basic metals, which are here in green, all the way from aluminum to livermorium. They are soft, brittle, and solid, and they have low densities, which is kind of weird for metals. And that's why they're characterized next to each other. And it just kind of worked out with the number of protons there as well. They behave like non-metals, and we're going to talk about non-metals in just a minute. And they can actually form bonds between metals and non-metals. So they kind of are like the linkage between them. That's what the purpose that they serve, especially when you build things and you need metals to be connected to one another. We go through a basic metal in order to do that. And most are bad conductors, even though they don't have an entirely filled p orbital. They don't have that sort of electrons in the d orbital, which are a lot easier to donate, especially because there's more excited states available. And again, they are from aluminum to livermorium, groups 13 to 16, periods 4 to 7. Oh, next we're going to talk about semimetals. A lot of people call these metalloids. I prefer either. I go, what's it called? There and back. I don't know, I'm like blinking. So it goes from all the way from boron to polonium. They are shiny, they are brittle, they are solid, and they have variable densities. Some of them are very high, some of them are very low, but they can form bonds between metals and non-metals. They behave like non-metals. The reason why they are not basic metals is because they're very, very good conductors. And this is just a trend among all of them. There's an explanation, it gets a little bit complicated, but all you need to know is that they're relatively good conductors. And again, it goes from boron all the way to polonium. There are 7 elements in here. This is where it gets a little bit tricky, but if you're able to distinguish, you're in a good spot. Next, we'll go to nonmetals. Don't forget our number 1 nonmetal, which is hydrogen. Nonmetals have very weak structures. They're very easy to break down. They're very easy to separate. They have high ionization energies, high electronegativities, high level of attraction to other nonmetals. We'll talk about what these two mean in just a second. And they're very, very important to biological life and organic chemistry. So they have no metallic characteristics. They cannot conduct anything. They cannot donate electrons to power, what we know as electricity now. But they're very important to biological life and organic chemistry. Most of our bodies are made from nonmetals, obviously. And that sort of bridge between what is a nonmetal and what is a metal is very, very clear. And again, hydrogen all the way to selenium here. Oh, I forgot to add a periodic table. And then we're going to go to the halogens. I'll show you where they are right now. They can be solid, liquid, or gas phase at room temperature. They are highly reactive, they are toxic to humans, and they are often found in a negative charge state. So the halogens are here all the way from fluorine to TS, which is element 117. And if you notice, if they are in a negatively charged state, if we add an electron, they will have an entirely filled p orbital. These elements are also diatomic. We'll learn about that when we talk about solutions and why they're important. Most of these exist in the liquid phase, especially most of you should be familiar with chlorine. This is what they put in swimming pools. And they're just an interesting group. They all behave very, very similarly. They're all very toxic and they're all highly reactive, especially when they're in their ground state. And then finally, the halogens were right here, all the way to fluorine, to tennessine. And then finally, we'll talk about the noble, I'm sorry, not finally, we still have 2 more after this. We'll talk about the noble gases right now. And they exist as gases. Who would have thought the noble gases are in the gas phase most of the time? They're very stable and they rarely react. This is all you need to know. And it goes from helium all the way to our 118th element. Noble gases. If I could be anything, I'd be a noble gas. And then we'll talk about the lanthanides, and then we'll talk about the actinides after, arguably like the two kind of craziest families on the periodic table. They mostly exist in solid form as far as the lanthanides, and they're rare elements. They've actually only been found on Earth once, which is just crazy in that they're on the periodic table and they're given so much importance and everybody learns about them. They're highly reactive and they emit harmful energy. They've actually killed a few people who tried to research them, which is really sad if you think about it. And of course, they're in group 3, don't forget, and they're in period 6. This entire square is representative of this entire row down here. And of course, we have our last family, which is the actinide series. They're not found on Earth, but they're known in the universe. Sometimes if like a scientist or some kind of representative of the science community, discovers something, then they will name them on the periodic table. It's kind of crazy. They are highly radioactive, can be created synthetically. And of course, the actinides are here. I'm not going to go into too much detail about the actinides and lanthanides. I want to save that for you guys to do if you choose to. Okay. So those are the families of the periodic table. Again, you are responsible for knowing some physical properties, chemical properties of them, and knowing where they are on the periodic table. Okay.